be the motivation for my whole approach. Indeed, you may recall from information geometry the basic example of the information metric of the univariate normal model, which up to a slight change of coordinates is the same as the Poincaré half-plane metric. So we have a striking connection between, on one hand, a fundamental object in statistics, and on the other hand, what is the fundamental example of a Hadamard manifold. We may accept this at face value as a fact, but of course, psychologically, we would like to ask why. Where does this come from? Is it a coincidence? And I'm going to argue that no, it's not a coincidence, it's a consequence of the fact that this information metric is what we call a warped metric. So look at the information metric. Whenever you see Z, it will be the couple X bar sigma. The information metric looks like a product metric. It's a sum of squares. But in addition to that, you have these coefficients like sigma to the -2 that depend on sigma, not on X bar. Roughly, this is the definition of a warped metric. And we will see the same remains true for a large class of location scale models. The information metric is a warped metric. Then our intuition is that the negative curvature in this example is only an instance of the general principle that you see written here. Warped products use convex functions to generate negative curvature. So in order to implement this intuition, I will follow a strategy, which is to replace the univariate normal model with its parameter space, which is the half-plane, by any location scale model defined on a Riemannian manifold. So the parameter space will be a kind of visually a generalization of the half-plane, except the fibers, they are copies of the manifold M instead of being horizontal lines. The question is, will the information metric down here continue to be a warped metric? In other words, does this square commute? And the answer is yes. This is the new theorem I was telling you about at the beginning. It says if M is in a reducible symmetric space, and if the location scale model is invariant to isometries in the sense of this condition, then the information metric is indeed a warped metric. Moreover, we know the precise expression of this metric, written here in blue, with coefficients alpha2 and beta2 that are given by these expectations. In appearance, these involve X bar through Z. However, they only depend on sigma, so they are well-defined functions of sigma. The proof of this theorem, which you can find in the extended version, is an application of Schur's lemma from the theory of group representations. And if you don't like the condition that M is irreducible, you can drop that condition. So then instead of a warped metric, you will get a so-called multiply warped metric. Having established this, I would like to digress a little bit and mention some general properties of warped metrics in order to then apply them to a specific example. So to begin with the definition, we are looking at a space that is a product space, just a Cartesian product. The half-line 0 infinity is called the base. The manifold M is called the fiber. Each one of these two has its own Riemannian metric. But then in addition to that, we have the function beta that appears in the metric here in order to warp or deform the metric of M. So we get a Riemannian manifold, which I call cursive M of beta. Now, this is only a special case of the definition of a warped product or warped bundle, but I won't go into that. So since the half-line 0 infinity is one-dimensional, any metric is a Euclidean metric. It's dr squared for some function r. And the significance of this r visually is vertical distance. If you have 2 points on the same vertical line, the distance between them is the difference in r. Let's look at this table, though, which is quite interesting. So as I said, warped metrics, they appear in geometry and in physics. And then the quantities r and x bar have different interpretations. For instance, in geometry, r is a distance function. It's the solution of a Hamilton-Jacobi equation. And x bar is a fiber point. Well, in physics, you have some other interpretation too, right? And what we would like to see is a new vision of warped metrics, which is a statistical vision, where r means dispersion and x bar means location. So we introduce a statistical vision of this mathematical object. Onto something more technical. In fact, the completeness and curvature of warped products is characterized analytically. For instance, M beta is complete if and only if both the fiber and the base are complete. Completeness of the base is equivalent to divergence of both of these integrals. The first integral is distance to 0, and the second integral is distance to infinity. So if they are both infinite, it's impossible to escape, neither from the bottom nor from the top. Hence, hence completeness, I'm sorry. For curvature, any sectional curvature can be found either from the Gauss equation or the Jacobi equation. If you look at the Gauss equation, if beta is a convex function of R, meaning it's geodesically convex, then we have negative radial sectional curvature, and this is the principle that convex functions produce negative curvature. Let's go on with our example, the von Mises-Fisher model. This is only an example among others. However, I chose what I thought would be most familiar to the greatest number of people. I hope I'm right in doing that. So here the fiber is the unit sphere, M. The model is an exponential model involving the Euclidean scalar product of x and x bar, and eta is strictly positive. So our parameter space is the product of a sphere and a half line, meaning it looks like the space Rn punctured at the origin. We don't know yet whether we can include the origin or not, but statistically the origin corresponds to the uniform distribution on the sphere. If we look at visually at our parameter space, the spheres become larger as we move away from the origin. And this is also statistically correct because eta is a concentration parameter. So as the densities become more concentrated, they are farther away from each other. So back to the question to what happens at 0, the coefficients of the metric, which we can find from our theorem, they are given by modified Bessel function. And if we take their functions and if we take their limit at eta equals 0, we see the limit value of the metric does not depend on the direction along which we converge to the origin. And this means the metric extends by continuity and even extends smoothly to the origin. And in conclusion, we have a bigger Riemannian manifold, which I call M hat. This is the whole of Rn, with the origin included, and equipped with the information metric. And we are going to see that this is a Hadamard manifold. So to begin, it's simply connected and it's complete, unlike the punctured space. Indeed, for simple connectedness, well, Rn is simply connected for any value of n. However, notice that for n equals 2, if we exclude the point at the origin, we lose simple connectedness. So you already see the importance of including the origin. Going on to completeness, we have our two integrals, distance to 0 and distance to infinity. The first integral converges, in fact, and this means that it is possible to escape our parameter space M at 0. But this isn't a problem because M hat contains 0, so that's not a problem for the completeness of M hat. The second integral diverges because we can look at an asymptotic expansion of alpha 2 as eta goes to infinity as a power series of 1 over eta. The first coefficient A is 0, so we cannot decide. The second coefficient B is also 0, so we cannot decide. And our last chance is the last coefficient. And luckily, this is non-zero, so we have logarithmic divergence of our integral, the distance to infinity. And this shows that M hat is complete, right? But M is not complete because the distance to 0 is finite. So we can now look at the curvature of M hat. So experimentally, we have seen that this curvature is negative. So indeed, M hat is a Hadamard manifold. Symbolic and numerical experiments have produced the same result to the effect that the sectional curvatures, well, for any value of n that we have looked at, n going from 2 to roughly 12, 10 or 12, the tangent and radial sectional curvatures have this negative profile, which decreases to a limiting value. So this is very pleasing because we can now see the space is indeed a Hadamard manifold. But of course, the question is why. In other words, how could we prove this? We have made an additional experimental observation that as eta goes to infinity, all sectional curvatures become equal. So our space starts to look like a constant negative curvature space. And it should be clear this is a manifestation of the central limit theorem. So statistical intuition, as eta goes to infinity, because eta is concentration, the model starts to look like a normal model. And the information metric of a normal model is a hyperbolic metric. It has constant negative curvature. So what we are seeing is interpolation between the uniform distribution at eta equals 0 and the normal model as we tend to eta goes to infinity. Again, eta is a concentration, not a dispersion parameter. So this kind of reasoning is general. Whenever you have a concentration parameter and a central limit theorem, the curvature interpolates between the two. So very quickly, there's also a full analytic solution of the geodesic equation. To find this full analytic solution, you look at conservation laws of energy and moments. And then you have a lemma here, which allows you to lift the whole problem to the Lie algebra of the group of isometries. As a result, the geodesic is separated into R, which follows a one-dimensional mechanical system, and X, which is a time-changed geodesic in the manifold M. So we know how to construct geodesics without any numerical computation in the warped product space. Now, as an aside, as a remark, a similar construction holds for Brownian motion in the warped Riemannian metric. And that's interesting because in the same way that we use natural gradient descent, we can also use natural diffusions to realize optimization. So it's good to know how to build a Riemannian-Brownian motion. In future work, our goal will be to develop the applications of this formalism. So the first application to density estimation, my colleague Yannick Berthoumieux will give a full talk about tomorrow. I will try to summarize the remaining three. To begin with regression, let's assume we have a learning sequence of inputs, xn, which belong to some input space, anything, and outputs, yn, which belong to the manifold M. To learn the relationship between these two, we start from a learning model where y is concentrated, is about some image, y bar theta of x, according to a location scale model. And this image is controlled by a parameter theta that is unknown. The learning problem is to find the best theta. So following the principle of empirical risk minimization, we want to asymptotically minimize the Kullback-Leibler divergence between the truth and the model. And this leads us to this cost function here. Now, what we know how to do is that we know how to compute the information metric of the learning model. And this turns out to be the average of the pullback of the warped metric. So we know the information metric of the learning model. And as a result, our problem reduces to stochastic optimization on a Riemannian manifold, which moreover is given its information metric. So we have good convergence properties with regard to efficiency. For the second application, we consider natural evolution strategies. So this is a problem of black box optimization on the manifold M. This means the cost function f is difficult to evaluate. The main idea is to implement search distribution which expresses our belief about the position of minima. Naturally, we take this to be from a location scale model. And then the core idea of NES is to replace black box optimization by classical optimization because we minimize an expectation or other probabilistic construction instead of minimizing f itself. So because we know the information metric, we have computed the information metric and we know it's a warped metric, we know the expression of the natural gradient, duality with respect to the warped metric, and any derivatives that appear don't imply the derivatives of f. And we can fully implement Riemannian gradient descent, meaning natural gradient descent, because we know the metric already, we know how to compute gradients, and we know how to construct geodesics, exact solution of the geodesic equation. So we're quite good with solving this kind of problem. And this generalizes known evolution strategies like CMA-ES to manifolds, to black box optimization on manifolds. I don't know if I have enough time to... All right, that's good, that's enough. Third application would be averaging of clusters, yes? So a cluster is a sample from a unimodal data population. So if we have some clusters like here, we can map them through maximum likelihood estimation to points in the parameter space of our location scale model. So if we ask the question, given several clusters, what is the average, most representative cluster? For instance, because we have too much data and we want to get rid of it, This amounts to finding a Riemannian p-barycenter in the warped product manifold M beta. Yes? So we can solve this numerically thanks to geodesic shooting. Remember, I have shown you we know how to solve the geodesic equation for initial conditions. We don't know how to solve it for boundary conditions, but we circumvent this by implementing the technique of geodesic shooting, because luckily we know geodesics and we know curvature, so we have no problem in solving this kind of problem, the average cluster, or in finding the distance between clusters, using also geodesic shooting technique. So now I would like to thank you for your attention, and this is a summary of some of the main points, and please go ahead with any questions. Thank you. Yeah.
So, what is the computationalization fee of geodesic shooting these days?
I'm not sure how to answer you. In geodesic shooting, well, I think the computational difficulty coming from constructing geodesics with given initial conditions is very weak, because we know analytically how to solve the geodesic equation with initial conditions. Now, each time we need to solve the Jacobi equation, and this is a linear second-order differential equation, so I guess because it's linear and we have well-known methods for solving like Runge-Kutta or anything, then it shouldn't be difficult to solve. I still would imagine, although there are people here who know this much better than me, like Alice, but I still would imagine on a laptop computer, it wouldn't run for too long. It would maybe take not more than, just a regular runtime of some. Yep. Yeah. Thank you.